Yes, yes. Most important question. Yes.
Next week, the only time these two are free is on Wednesday, but I have exam like full week, so I want to postpone it to the week after midterm. So our CMI midterm, because I have all day exams.
You have all day exams?
No,
Oh.
I have exam throughout the week.
Okay.
So I want to postpone it to the week after. Request.
Yeah, I'm not averse to that idea at all. Provided, how about Saturday next week? Yeah?
He won't be there, but
Oh, you won't be here, okay. So the week after that, that's fine. Sometime in the, how many of you want to take the exam? Okay. Mitra, did you raise your hand or no? No. Oh, you haven't decided, okay. But we'll just, okay, we'll decide the exam without taking you into consideration, and you're welcome to take it if it suits you.
it's not compulsory.
I know. For her, it's not compulsory. Yeah. So we'll leave her out of the calculation, and she can take it. Anybody is, you're welcome to take the exam even if you don't have to. Okay. And I'll give you my feedback. So tell me.
After he comes back from home is fine. Like he won't.
When are you back?
So I'll be back on Thursday. The Wednesday is anyway holiday, so
Which Wednesday is holiday?
or the week after next.
Week after next. What is Wednesday? It's a Mahal Amavasya holiday?
2nd October. 2nd October.
Oh, Gandhi Jayanti. I see. 2nd October is a holiday.
So
Okay.
Friday,
So 4th October.
yeah, 4th October, Friday, it's possible.
4th. I don't want to miss class maybe.
Okay.
So some other time. Some time we'll fix.
Sure.
Huh?
Afternoon slot.
Afternoon slot on Friday.
Sure.
Sir.
No, we have an algebra class.
When are you free? When can you make it in the afternoon? I want say 2.5 hour gap.
We can have it that Saturday if you're okay.
That's fine.
No, Saturday I have class.
So you have class here?
Yeah.
What time?
Morning and Balu's class. So
Yeah. What time is the class?
starts at 11 up till 1, and then after lunch there's one more class that start usually.
Okay.
I guess it will be a problem like for
No, how about 9 to 11 on Saturday?
Oh my god.
No?
let's have it on the Friday after next week from 4:30 to 7:30. I guess we don't time.
Okay. Maybe 7:30 is too much. Maybe.
2 hours exam.
No, Friday, when are you free?
So 3:30 class gets over.
You can come
Okay, in CMI?
But yeah,
You
Three-
can come here by 4:30. You can start from 4:30, right?
You can come here by 4?
3:20 shuttle if you guys get come here by 4. Like 4. Yeah, around 4 you can come.
Fine. Fine. Let's fix it for Friday, October
4th.
4th. Fine. That will suit me fine. Okay, tentatively, so October 4th, Friday afternoon, let's say 4 o'clock. I mean, if you're late by 15 minutes, that's okay, because the shuttle is late. And next week, can we have class or no?
Friday is possible.
I have exam.
Yes.
What time? What time?
I have exam from 9:30.
On all days?
Yeah, Thursday is not an exam, but we have a take home exam.
But that's okay. So can we have class? The question is, can we have class on Wednesday and Friday or not?
So we can have. I prefer not.
Okay, fine. But
When they have no class, no exam on Wednesday, I guess. You can have class next week.
we can. Why don't we then have class next week? Okay. So anyway, I'll confirm that to you by email. Okay. So as of now, we are having class next week as scheduled. But if there is a change, I'll send you email. Okay. But Friday you don't want to have.
No, Friday is possible.
It is Friday class.
Wednesday, Friday classes are okay. Okay. Fine. Okay. Okay. Thank you. So I'll as of now we are having classes. If there is a change, you will get a mail. Okay. Good. Okay, okay. That's now that the important question is settled. How about maybe some math question if you have any?
So you said last time that the semi-simple part of this GLN K for any algebra that will be dense.
In GLN.
GLN K. So I don't see like clearly how it is dense. Like
Okay.
for C it is okay, like for C complex numbers.
Ah.
But for arbitrary algebraic groups,
Yeah, so we did that. So here is a sort of proof for that. Okay. So consider regular semi-simple element. Do you know the definition of that? It means semi-simple element with distinct eigenvalues. So that's semi-simple. Okay, that's not a kosher definition in the sense that there is a notion for any algebraic group. Okay, so you have to. This is just for GLN. Okay, so we are so k equal to k bar GLN k. Just 1 second, I have to take this call. Let's look at, so these are given by, so this is defined by, this is an open set. Defined by the non-vanishing of the discriminant of the characteristic polynomial. So if you have a polynomial, right? So if you have a polynomial in one variable, there's something called the discriminant. Okay, what is it? It is, you know the definition of the discriminant? Pardon me? Product of the roots. Not quite.
whole squared.
Not quite. Say that more correctly. It has something to do with the roots, surely. So it must vanish if two roots are equal. So what would you like to have? So it is, so what is it for a quadratic equation? So quadratic polynomial, monic quadratic polynomial, t square plus b t plus c, b square minus 4ac, right? What is that? What is b square minus 4ac? The roots are minus b plus or minus root of b square minus 4ac by 2a.
Difference of the root square.
Difference of the roots square, right? So what you do is, if so discriminant is if alpha 1 alpha r are the roots, or let's say alpha n are the roots, alpha 1 minus alpha 2, alpha 1 minus alpha 3, alpha 1 minus alpha n, then alpha 2 minus alpha 3, alpha 2 minus alpha n, alpha n minus 1 minus alpha n. Okay. Why do you put a square there? If you don't put the square there, what's the problem?
It won't be symmetric.
Yes. So the reason why you put the square is because it is symmetric in the roots. That is, if you switch, if I write alpha 1 minus alpha 2, for example, why should even in the quadratic case, b square. So if I take, why should I not consider square root of, why should I put a square, right? If I take the difference of the roots, that only gives me, so that's not symmetric. If I switch the roots, okay, so this has the property that it is a polynomial in the coefficients of the equation. Okay, so this is a polynomial being symmetric. In the roots. It is a polynomial in the coefficients of the original polynomial. E.g., if we have p square plus b p plus c equal to c is the form. Discriminant is okay. Now it has the property that when it has this beautiful property that it defines for you, you take that polynomial. So this is the locus of values. If you think of this as a function of b and c, this is the non-vanishing of this is precisely when this equation has distinct roots. Okay. Now look at this. It's this okay?
Okay.
Okay. So so now think of this. The characteristic polynomial has polynomial coefficients in the original polynomial x1, 1, xn. Now you take it has some degree, n degree n. Okay. Now you take the discriminant. The discriminant is a polynomial in the coefficients. So you write, you will get some big polynomial whose non-vanishing will tell you that the matrix has distinct roots, distinct eigen, and therefore those will have distinct eigenvalues. Okay? All right? Okay. So which means that this is an open condition. It is the non-vanishing of a. So, and open sets. So maybe I'll say this. So well, there it is. This I have looked at a subset of the semisimple elements, namely only regular semisimple elements, right? And that set is an open set. And it's an open set where it's an open set in an irreducible variety. GLN is irreducible. Okay, because if you wish, it is an open set inside a affine space which is irreducible. Okay? So therefore it is dense. So alright. So thus regular semi-simple elements form a dense open subset and therefore dense because your variety is irreducible. Okay, so in particular, semi-simple elements are dense.
Are they also open?
I don't think so.
They are not open for C.
They are not open for C. If they are not open for C, what's the example? How do you see that it's not open for C?
You can take the identity and take a corner element. You can change it by epsilon, then it won't be semi-simple.
So you're saying every neighborhood of the identity will have a there you go. Good. And if that's a proof because if it is not open in the usual topology, it can't be open in the heuristic because that's weak. Okay, so that's a full proof. Okay? No, this is something you should definitely dwell on this and understand because this may not appear as what to say in the book. This is not for, if you go to the next level of algebraic group course, this will be assumed. Okay, this forms part of an exercise for a regular elementary course like this. Okay, so if you come to the next course, people will tend to just say, this is because of this, and then they just go on. So this falls in sort of this is something for you to sit down and get it. And by all means, you should think about, what is it in the usual topology? What is it in the, don't let your thought process, of course, you should understand the book line by line and follow the reasoning of the book. Okay, that's another way of thinking. But you should not limit yourself to only that way of thinking. You should relate it by all means to other things that you have learned. Okay, so what is it in the usual topology? What is it, what is it for complex numbers? What is it for finite groups? All these things you should sort of complete your form as many connections with whatever you know as possible, because right? Good. Okay, so let us continue with our chapter. We're doing chapter 3. Groups and Torah is the title. And the one theorem that we will not do, but it's important, is that if you have a linear algebraic group connected of dimension 1, then this implies there are only two possibilities. Okay? And I repeat, we will not prove this in this course. Okay, so we were doing structure theorem for diagonalizable groups. That's what we had. So the following are equivalent for a linear algebraic group G. And what are the three things? One was so let's recall, one was sort of that it is diagonalizable in the sense of the term diagonalizable. It's a closed subgroup of some D. Okay, that is the first. D is a closed subgroup of some Dn, or Dn for some n. Dn, of course, denotes n cross n invertible diagonal matrices. Two was a characterization in terms of the coordinate ring. Okay? So you look at the character group of G. This is the group. As I said, it is all algebraic group homomorphisms from G to Gm, and it gets a group structure. It's an abelian group structure which we write additively, is finitely generated as an abelian group. And Kg is spanned by and spans as a K vector space. And thirdly was a representation theoretic characterization. Namely, every rational representation is a direct sum of one-dimensional representation. Every rational representation of G is a direct sum of one-dimensional. And we had one implies two, three implies one, two implies three was the more difficult part, but maybe there were a few things that were not said on the board, but I am not going to worry about it. Okay? It's considered that the proof is complete. Now let's move on. So we have defined and said something about this part of the type, diagonalizable groups. Next is Torah. Okay, but before that, point 2.4 corollary. If G is diagonalizable, X star G is an abelian group of finite type without pre-torsion if characteristic K equal to P is positive. The algebra Kg is isomorphic to the group algebra of X stars. Okay, let's see proof. Why is it a abelian group of finite type? Well, we did that as part of our right? G is contained in Dn. Therefore, there is a map which goes this way. The restriction map, and we showed that it is on. This was what we showed. That was part of the proof that one implies to.
Finite type means finite generated.
Finitely generated ability.
That is part of the statement of Socrates. Extra G is finite generated.
Very good.
Only the pre-torsion.
Yeah, only the pre-torsion. Yeah, that's correct. Yeah. So you can say that, yes. Okay. So the second part, he says, follows because K does not have peak roots of unity. So let's see, if you have, why doesn't it have pre-torsion? Okay. If so, why isn't suppose characteristic K is equal to P is positive and chi is in chi star P with chi to the P equals 1. Okay. Pre-torsion meaning P chi is equal to 0, which is the same as chi to the P equal to 1. So that means chi of G to the P is equal to 1 for all G. But if in a characteristic P field, this is an element of the field, its P power is 1. That means this must itself be 1, because you can write this to the, so it implies chi is 1. Okay. Now, why is this true? Well, chi star G spans Kg as a K vector space, correct? Moreover, by dedicant, it is actually a basis, right? And so Kg you can write as K X star Z. Okay? By 2 there. Kg by 2 and dedicant kg is equal to k chi star as a vector space. Now you can check that this is as an algebra this is. So this thing will be a algebra morphism. Okay. So what do we have to do? We have to check that if it's both are pointwise multiplications. Okay. So it's sort of built into the. Now, so this gives us some way to make diagonalizable groups. Okay. What we are going to do therefore is this shows, and we will the next section makes this explicit, as he says, is that there is a equivalence of categories, if you wish, between diagonalizable groups on the one hand and finitely generated abelian groups without pre-torsion on that. That pre-torsion you can forget if you are in characteristic 0. It is just finitely generated abelian groups in characteristic 0. In characteristic P, you would have to leave out groups with pre-torsion. Okay. What is the isomorphism? Well, you just take the group and form its group algebra. Okay. So that is the one-to-one correspondence between. Since it's to the group algebra, it is covariant. To the group, it is contravariant. So the next section makes this explicit. Okay, so let's see. So if M is a finitely generated abelian group, then what can you say about the group algebra of Km? Okay, now I am violating something that I did say about notation. Namely, I said that I will always write the group algebra without the square brackets. So I'll go back to my, let me try this. Okay, let's look at that. What can you say about that? Is it it's a commutative algebra? Because M is abelian. Okay, it's a commutative algebra. So I want to try to make it a half algebra of the correct kind. Okay, so I want it to be reduced. Right? And I want it to be affine algebra. So is it an affine algebra? to say it's affine, I must have finitely many generators. Where are those finitely many generators? The generators of the abelian group. Right? The way it is made into. So, mind you, this group is now this finitely generated abelian group. The abelian group you might write additively, but when I write Km, I'm thinking of it as multiplicative. Okay, I'm doing this without tacitly. Okay, you have to make that adjustment in your mind. Okay. So the fact that is why I am taking a finitely generated abelian group. The reason why I am taking a why I am not taking arbitrary abelian group is because I want an affine algebra. Okay, so this is an affine algebra. It's an affine K algebra. Now, okay, let's see why it must be so. Assume M has no p torsion if characteristic of K equals P is bigger than 0. Okay, so why do we put that condition? Okay, let's see if so let's see. I want to prove. He doesn't mention this, but I want to prove that this is reduced. Okay, so how do I prove that it is reduced? So if surely this is required. If I have a p torsion element in M and the characteristic is P, this is going to be this is going to become non-reduced, because I can take an element, we call it G to the P will equal to 1, so G minus 1 to the P will become 0. Okay. Now, so the claim now is that if I'm away from that problem, then it is reduced. This I don't know why he mentioned, there's no mention of that, but that should be true. So let's see why it is reduced. At the moment, I don't immediately see it, or want to say, but it must be true. Okay. So, question. I'll put it as a question. Km reduced. So my thought process is slightly different from the book here. Okay. What I am trying to see is that we have identified, as we did in the one of the early lectures, that the category of linear algebraic groups is the same as the category of half algebras with underlying algebra being reduced and affine. That's the okay. So given M affine, so I'm trying to make this into this group ring into an algebra which is reduced and affine. Okay. Now group ring is always a half algebra. So you have to define. So it's an algebra. It's algebra structure comes from the group structure of the group. Now, if I want it to be commutative, I am forced to take, or it's natural to take M to be commutative. In fact, I am forced to take M to be commutative. Okay. Now, to be reduced, I have taken this, and I think that should be enough. Although I don't see a proof of that. Okay. So I have a reduced affine algebra. Now, how is it a half algebra? That part works in general. So if you have a group ring, it has a natural structure. Group ring now in the sense of KG. Okay. So here is a statement. So for any aside, for any G, KG is a half algebra. How? Well, to make it's an algebra, that part is no problem. It's an algebra with identity, with unit. So I have to only give you the co-algebra and the co-unit maps. Okay? What should they be? In fact, it is something that you know. So I have to write a co-algebra, right? Okay? So co-algebra means what? Co-algebra means I have to write this delta. Okay? Question is, what is this delta? Now, if you recall, what is the point in having a coalgebra? The point in having a coalgebra is that you can take tensor product of modules. So I repeat, if M is an A module, then M tensor M is not an A module. M tensor M is naturally an A tensor A module. More generally, if M is an A module and N is a B module, M tensor N naturally becomes an A tensor B module, but does not become, M tensor M does not become an A module. However, if you have a map, algebra map from A to A tensor A, then this M tensor M structure of A tensor A you can pull back to E. So the reason, now of course it has a life of its own, but at least initially the reason for having a coalgebra map was to get a tensor product structure on your category of modules. Okay? And what is the point of having a co-unit? Is to have the notion of a trivial module. Okay? If you have an algebra or a ring, what is a trivial module? Doesn't make sense. If you think about it, doesn't make sense at all. Okay? So to say something, so if you have a map from R to K, which is an algebra map, K being the underlying field, all objects being vector spaces over K. If you have an algebra map from your ring to your K algebra to K, then you can use that to make K into a R module, and that will be your trivial module. Okay? So I repeat, so although trivial module is something that we use naturally, because, so what I'm trying to say is this coalgebra structure and this co-unit structure is, when I said that you know it, I said it because you do it without thinking. If you have a group, namely you naturally take tensor product and you know that how the group acts. Well, it acts by GM tensor GM. So naturally the coalgebra structure must take G to G tensor G. So why is this well defined? Well, this is a basis for, so this defines, so then you do it linearly. Okay, it's an algebra map. It must be an algebra map. So in particular, it's a linear map. Therefore, it's enough to define this one, basis elements, and this is the definition. And you can check that it works. Okay. And similarly, what is the co-unit? So I must have a map from, right? So this way, you think of this as giving the trivial module structure. So if you have a trivial module for a group, what does it mean? Every element of the group acts like identity. So G goes to 1. Right? And what is the antipode? So you also needed an antipode for half. So what is the antipode? That's the antipode. Right? So we have this for free in Java. Right? So indeed we do have this, and the only reason why we cannot say take spectrum of this, for example, is because we don't know what the spectrum of a, I mean, of course these days maybe people have started giving it meaning, but we don't know what the spectrum of a algebra which is not commutative means. Okay? So, but the moment, now but if you are in this situation, this becomes an affine, commutative, affine K-algebra. And if I have this condition, then it's even reduced. So I'm in business. I can just take that group ring and take its spectrum, and lo and behold, I get a linear algebraic group. Okay? So starting from an finitely generated abelian group without pre-torsion, if the characteristic is positive, has positive characteristic, if the field has positive characteristic, I do get a linear algebra. And how do I recover the group from the, is this process, so is this process, is there a loss of information, or can I get back my group that I started with? Well, given my linear algebraic group, what do you do to get back your group? What might you do? You take the character group. You take the character. And so this procedure of going, so on the one hand, you have finitely generated abelian groups without pre-torsion if characteristic of K equals T is bigger than 0. So K equal to K bar. That's our base. So you have on the one hand this, and you have diagonalizable, and it goes, so I can take this and it goes into the category of diagonalizable groups, because I have, okay, so let us see if I form this, right, what are my characters? So let us see that M is actually, given an element of M, how is it going to be a character of my group, right? Okay. So M is a function, right? M is an element of this, which means it's a function, right, on the group. That function is the character. Okay, so we have to check that. So let's see. So M let's check this. So I'm trying to give this map. Okay. So M why is it, have to check that it is a morphism, okay? So let us check that it's a, why does it go to, it's a, being a function, it only goes to k. Why does it go to k star? Right? So it goes to k star because there is a minus n. So I know that m minus n equal to 0, which means the function m of x into minus m of x is equal to 1. Right? So I'm going between, so let's type this maybe as so indeed, so it is an element, it's a unit in this algebra. M is a unit because every group element is a unit in the group algebra. Okay, why is it, so we have to check that m of xy is equal to mx my. Let's see why that is. Okay, x and y you think of as maximal ideals in of this. This should also be obvious. Let's see, mx y is equal to mx times m. Well, that follows from this. Okay? Because how do you multiply two elements of the group? That comes from this structure. Okay? Okay. So here, this is a very good exercise to for you to get everything clarified. Okay? So you should work through this. Everything works as expected. Okay? But you have to think, it's a good exercise to think through what this means, what every little detail means. Okay? So all I'm saying is this comes from this. Why? Because there is a multiplication of the group here. That multiplication of the group comes from the coalgebra structure on the algebra, on the half algebra. Okay? So I will leave this. So so you do get, and this will be an isomorphism. Okay, each element of M will be distinct. So this is an injection. There are different functions. So there will be distinct characters. Now they are all characters because if there is any other character, it is a linear combination of these. Therefore, any character must be one of them by dedicate, and so on. So there are lots of. So the claim is that this is an isomorphism. Okay, that is also clear, but you should think through that. Okay, so the point is, on the one hand, I do get Km is a diagonalizable group, a spec of that. So if I take M here, the map I do is spec of Km. And as Gautam might complain that it should be M spec rather than spec, so I will not, your choice. If you prefer M spec there, by all means take it to be M spec. Okay? And if I am given something here, how do I, so given G here, I get back. So this is a equal, whatever you want to call it. This is a bijection that preserves all properties. Okay, you have group homomorphisms here, which will give you algebraic group homomorphisms on the other side. Why? Because if you have group homomorphisms, you will get algebra maps from this to the other, which will also satisfy this condition. There will also be coalgebra as maps of coalgebra, so you will get in fact maps of varieties because they are maps of algebras, and those maps of varieties will be maps of homomorphisms on the underlying groups because they are maps of, because the co-multiplication is also preserved. Okay, and so on. There are details to be checked, but it's all pleasant and it works out as it is expected to be, and I leave that. Therefore, so the statement is that you have this equivalence of, I just say equivalence. He says there is a canonical isomorphism M to chi star Gm, and if G is a diagonalized group, there is a canonical isomorphism of. So if you start with something here, you go back and come to the spec. He says there is a canonical isomorphism between, meaning that if you do for another one, and another one, etc., and then you can line them up. Okay? In other words, that's just a very fancy way of saying that if you go there and come back, you get back to where you are. Okay? This is an intuitive statement. If you want to make this precise mathematically, then you have to say there is a canonical isomorphism. Okay? It just means that you go and come back. If you have a, just theoretically, if you want to say it, it's the identity map on this set, if you think of it as. Oh. Let's see. So much for diagonalizable groups. So on the one hand, we had those three definitions, which we call the structure theorem for diagonalizable groups, but we have even more. Okay, they are determined by their character groups. Okay, you just take the character group, take the group algebra, and take its spectrum, and then you have. Okay. Now, so the other term in the title of this chapter is tora, which is plural for torus. So what's a torus? Okay. So torus is a linear algebraic group isomorphic to some D. That's the definition. So this is the definition.
After this equivalence of categories, so if I start with some two groups and end up with the same character, if I take the X star and get the same character, isomorphic character groups, So then I can conclude that the original groups that I started with are,
Yes.
I mean,
Yes.
diagonalizable groups. They will be,
No, say that again.
start with two diagonalizable groups, take their characters, and if they are isomorphic,
Yes.
so that means
Yes.
as lags there is a
Yes.
morphism.
Yes. They are isomorphic.
Yes.
Yes. It would follow. Because once you have an isomorphism here,
That
it would follow that there is an isomorphism. Of course, you can try to construct it ab initio by if the character groups are equal. That means you will get see this character. I mean, of course, it's the same as this, but you can write that so you see because KG has basis the character group. So you can set that. You can line them up, and then prove there, right there, that that's an isomorphism of half algebras, and therefore, yeah. But that's, yes. So the point about diagonalizable groups is that they have lots of characters. And it's very special to diagonalizable groups, or if you are working with connected groups, then you will see that the diagonal groups are nothing but tori. Okay. So they have lots and lots of characters, enough to span the ring of functions. Okay, that's very unique to. I mean, it's the same as being a diagonalizable group. So it's equivalent to being a diagonalizable group. If you take something like GLN, for example, what is you might want to wonder, what are the characters of GLN? Okay, I'll ask that and you think about it. Okay, it has very few characters, or even better, S7. What are the characters? Okay. So that's a question. You can wonder about that. Okay, corollary 3.2.7. Corollary of all the considerations above. We'll not worry too much about what it is a corollary of. Let G be a diagonalizable group. Then G is a direct product of a torus and a finite abelian group of order prime. G is a torus if and only if it is connected. G is a torus if and only if X star G is a free. Okay. They might sound like quite a lot, but it's in fact part of what we have proved already.
Is a torus the same as GM cross GM? As groups, they are the same, but are they the same as varieties?
Yes, they are the same as varieties. So Dn is that is an isomorphism, right? Dm you can no.
T1, T1, T2.
Yes, Yes, that's a, yeah, Dn is isomorphic to Gn cross Gm cross Gm n times. That's more or less obvious. But okay, so how do you do the first one? Oh, okay, or last one. G is a torus if and only if. So that's in fact what Gautam said. What is the character group of a torus? We did that last time. Z power n. And if it comes out, if you take a diagonalizable group and it comes out to be Z power n, then if it's free, then it should come out to be Z power n. Because you know it's finitely generated. And on top of that, if it's free, it's Z power n. And therefore, it must be the same as the torus. Okay? So it's okay, so that follows from about 1. Again, pass to the other side. Okay, here is a question. Suppose I take a finite abelian group, right? I take a finite abelian group, take its group ring, right? Take its group ring, and take its spectrum. Right? What do I see? That's a nice question in itself, right? I take a finite abelian group, take its group ring, right? It's a commutative algebra. It's a finite dimensional algebra. I can take its spec. Commutative algebra, finite dimensional, so it's in particular it's an affine algebra. I can take its spec. What do I see? Okay, the point is, okay, it is going to be some, so that will have some structure, right? It will have some structure. Right? So, whatever it is, so that it's going to be finite. So the proof of this, okay, let me say this, the proof of this is the following. Proof of this. So I want to say G is a direct product, right? So go to the other side. When you go to the other side, you have X star G, which is a finitely generated abelian group. So you write it as a free part, direct sum, a torsion part. Then on this side, when you come back, you get a torus, cross. So a few things to be observed are, in this association, M going to Km, so if I have K of M1 direct sum M2 is what? What do you want to write here? In terms of Km1 and Km2, what symbol should I write here? Tensor. I should write a tensor. Okay. Now, so if I take spec of this, in terms of spec of Km1 and spec of Km2, what symbol should I write here? This is a Cartesian product. Right? So the Cartesian product on affine varieties is the same as the tensor product on their rings of functions. Okay? If you wish, that's how that's how the Cartesian product of varieties is constructed formally. In any case, so you have this. So if I break up, so the point is, if I break up my thing as direct sum here, it becomes a product. So I write my G, X star of G as a free part, direct sum, a torsion part. Now, this part, the free part will become the torus cross. That part will be a finite group because it's a finite algebra, finite dimensional algebra, whatever it is. It's a finite dimensional algebra. Okay. Now, it's a finite dimensional algebra which is, therefore it's a finite group. Okay. You have to say that it does not have p torsion. Right? That's the extra part. Okay. That amounts to, there is so it is part of the question. Suppose I take a finite abelian group, do this procedure, I get a linear algebraic group, which is actually a finite group. How is that related to the original finite group? The point is, I will only make this statement. I will not spoil the suspense for you. I will let you work this out. So this exercise is start with a finite abelian group. And assume, if you wish, that, so let's call this F, keeping with this notation, that M has no p torsion if characteristic of K equals P is bigger than 0. And as always, we have K equal to K bar of E. You're over some algebraic field. What is spec of Kn as a group? So Kn is a finite algebra, finite dimensional algebra, therefore its spectrum is finite. And we have, so this is a finite group. And the claim that I want to make, I will not give you the answer, but if this has no p torsion, then this has no p torsion. So it's if and only if. Okay, so that answers this. Right? Because, okay, to do it, so if the G is a, I take my G, I take X star G, write it as a, X star G is some free part plus a finite part without p torsion. Now to get back my G, I have to just take spec of this, and when I do, I get spec of this, cross spec of this. This gives me the torus, cross. This gives me some finite group, and the claim is, since this had no p torsion, then this has no p torsion. That's that. Okay. And how about this?
Originally, why does Z not have P torsion?
Because
No, no.
we have already seen
We take X star G.
Extra it is not.
X star G has no P torsion, because if you take a character whose power is equal to 1, then the character must be equal to 2. Never mind, it's good always to think. See, you know, at least personally what I do is I try to, you know, it is good not to quote theorems always. Theorem is in a flow, but you have to, it's good, you know, don't put yourself down. It's good to question, keep asking and keep repeating those arguments in your, going over those arguments. That's how one learns. So how about this? If and only if it is connected. Okay, so let me ask you, so let's ask the question. Suppose I take an affine variety. When is it, okay, so G, let's ask when it is irreducible. In terms of the coordinate. So this is some commutative algebra. Right? There is a one equivalence of categories between reduced affine algebras and affine varieties. So, in terms of the property of an algebra, when is a variety irreducible? When the thing is a domain. Right. Absolutely. When the thing is a domain. Now, G is an algebraic group, so connected or irreducible is the same. So G is connected if and only if Kg is a domain, right? But Kg is equal to K of some free part cross K of some finite group, right? So the K of the finite group will never be a domain. Will never be a domain. Okay? Why is that? Because if it is a, you can show that if you have a, okay, here is another commutative algebra. Okay, or let me ask you, why isn't it a domain? It's sort of similar to a finite integral domain is a field. It's sort of similar, but you have to use some other argument. You have a K, you have K, you have a finite dimensional algebra over that. Claim that is not a domain. Okay, that's a good exercise. You think about this. Okay, so you have to use. Okay, I'll keep quiet. I'll let you. This is just commutative, plain commutative algebra. This, if you've seen at McDonald, you should be able to do this. Think about it. Of course, you have R contained in C, right? You have R contained in C. So C is a finite dimensional algebra over R, and C is a domain. So it's not going to work if the field, I'm using the field is algebraic groups. Okay. So now modulo that, is this clear? G is connected if and only if it's a torus. Why? Because take G, it is connected if and only if when I go to the other side, when if it's group ring, if it's group Kg. So here is the so proof of 2. 2 there, yes, 2. Okay. G is connected connected if and only if G is irreducible. Because it's an algebraic group. If and only if Kg is a domain, or K of G is a domain. Correct? If and only if K x star M G is a domain. Okay? If and only if K x star G free part cross K tensor K x star G finite part is a domain. Okay. If and only if x star G finite part okay. If and only if K right? So I am claiming this is never a, this can never be a domain. Okay, that's the part you have to do. So the only way it is a domain is that it's trivial. It's just K. Okay. So modulo this is this clear? Modulo this. Okay, and there are a few more things which are interesting. So the next thing is called the rigidity of diagonalizable groups. Okay, that's again a very beautiful statement. Okay, it says the following. So you take the automorphism group of an algebra, a group of automorphisms of an algebra. So you can take automorphism group of any object in any variety, right? In any category. In any category you can take the automorphism, right? So it's a set of all isomorphisms from that. Now, I mean, you can ask whether this what kind of a structure this has, right? Whether this automorphism group has itself the structure of a variety or not. That's this question you can ask. Okay, but never mind. What we will show is that okay. So here is the point is this automorphism group, whatever it is, cannot have, intuitively speaking, a continuous part. That's the statement. Why not? The intuitively the answer is clear. The answer is the following. If an automorphism group acts on the torus, or a diagonalizable group, it acts on the, it's the same thing as the automorphism group of the underlying character group. But that's discrete. Therefore, if you buy this argument, okay, this is not completely kosher because you have to say that that map is continuous for this to be. See, you can't have a map from a, if you have a continuous map to a discrete group from a connected group, then it must be constant. Right? This is what you want to use. So you can't have. So this the you can't. So for example, GLN. So you can think of GLN acts on GLN by conjugation. That acts like group automorphisms. Right? So it has a connected group which is acting. Okay, you might say GLN, there is a kernel, but SLN or PGLN as it's called, GLN modulo its center acts on GLN as a group of automorphisms. Okay, so it has a connected group of automorphisms. Okay, but you will see that the point is that if you have a torus, or more generally a diagonalizable group, it cannot have a connected group of automorphisms. Okay, and the proof is really this, that it must act, see, somehow the diagonalizable group is determined completely by its character group, and if a connected group acts on this discrete, this connected group is forced to act on this discrete group, and therefore trivial. Okay, this is the argument, but that is not kosher, since it's not completely, you will have to give it, you will have to, to make this statement, you will need some continuity statement on the maps involved. And since you cannot get that sort of, that is difficult to make it up, the proof will, sort of circumvent this problem and go in a different direction. But I want to emphasize that this is all that is. Intuitively, all there is that it is determined by some discrete, since the group is determined by some discrete data, and there cannot be an connected automorphism group of that discrete data, you are wrong. This is in fact the proof. But that's the intuitive proof you can have in mind. It's not going to be the official proof. Official proof will just do something and ask you to look at something and say, where you can't. Okay? Okay. So we'll do that next time. And there is also a little more on one parameter subgroups and limits of one parameter subgroups. Those are very interesting things. So I would like to, so I thought I would, today is already Friday, yeah, I thought I'd be done with chapter 3 today, but never mind. So we'll, one more time and we'll be done with chapter 3, and then we'll go on to chapter 4, and there we'll, again, maybe the difficulty level will maybe raise once again, because then we go into differentials, separability, derivations, etc. So it is, you will need to keep working. Okay? I'm not trying to scare you, I'm only trying to sort of help you out to work. Okay, see you then on Wednesday next week. As of now, we are having it. If there is any change, I'll send out.